There's going to be a few times in the course where I tell you about one particular reaction and then immediately offer you another tool that allows you to accomplish the same thing. And you might be wondering to yourself, well, why do we have multiple such tools? And in this particular context, if you know anything about mercury, you're going to ask yourself, why would you ever do a mercury-based reaction? It's an expensive reagent. I mean, sulfuric acid is incredibly cheap, so mercury is way more expensive than sulfuric acid. Mercury is very toxic to the environment. It will kill fish and do all sorts of other bad pollution type things. It can kill you personally. There have been multiple researchers that have died as a result of organomercury spills, rather famously in fact. So why on earth would you ever use mercury when you have a cheaper, better, less toxic, safer alternative? Sulfuric acid is no one's idea of safe, but it's better than mercury. Well, more or less because you can have bad things happen if you run the reaction this way. So it starts the way you'd expect. The double bond will go ahead and attack the sulfuric acid, and that will then lead to the secondary carbocation, which is precisely what you'd expect at this point. And of course, the water is the thing that you would expect to attack next because it's the nucleophile, it's the solvent, you have a lot of it floating around. So you've generated a secondary carbocation, you would expect that to immediately be trapped, and of course that will in fact happen. Now that the water has gone ahead and attacked, of course, then you can have another molecule of water and the solvent come by and do the deprotonation, and so your final compound is going to be the racemic mixture of alcohols that you wanted and that you expected. You're happy, everything's good. And of course, that racemic product is hopefully what you were trying to make in the first place, and you've gone ahead and made it, and there's no problem. But that's not the only thing that can happen here, because as soon as you generate a full-on carbocation, you recognize that this is a secondary carbocation, and right over here, you have additional stuff. So what if you do an alkyl shift of this variety? Well, then the result of that step would be that you have now created a tertiary carbocation. So this methyl slides over. This methyl had a cation on it and a hydrogen, but now you have two methyls and a hydrogen. This position where the methyl was is now missing a carbon or hydrogen or fourth bond, so it now has the carbocation. So what you've done is a rearrangement, and this is explicitly downhill in energy because you have a secondary carbocation becoming a tertiary carbocation. And of course, that will then immediately be trapped by the water, as expected, and so after a acid-base step with another water molecule, you end up forming the rearranged product. The rearranged product is in fact a chiral, and you only make one of it because there's only one thing there, but bear in mind that you were presumably not trying to achieve that. You were instead trying to make this racemic alcohol, and so this is a nasty byproduct that you are trying to avoid. And unfortunately, the problem is that you really cannot prevent it from happening. The reason why this product will exist and show up in your reaction is because you need to go through this carbocation in order to accomplish the transformation that you want. And as soon as you generate some of this carbocation, it can immediately rearrange to form the more stable tertiary carbocation. And so in some sense, you cannot avoid making this if you are trying to make this along this mechanistic pathway. If you are just using simple acid, it doesn't matter which acid you use, all paths lead to this cation, and then this cation can rearrange and give the wrong thing. So how would you avoid doing this rearrangement? How would you avoid making this tertiary alcohol? Well, you can't have a secondary carbocation at any point in the mechanism. Therefore, you need a mechanism shift. You need to have a reagent that allows you to generate the equivalent of a carbocation at that position without, in fact, having a full carbocation. Because if you don't have a carbocation, then it can't rearrange. So what you do instead is you use mercury, and the mercury will go ahead and now, at the same time that it's being attacked, it will add back in while ejecting one of the ligands. And so now what you have is formally not a cation at all, but a mercury that's sitting on top of both of those carbons simultaneously. And because you don't have a full-on cation, there's no driving force for the alkyl shift. And in fact, the alkyl shift would then cause some other problems potentially to take place. So in fact, nothing happens other than the reaction you want, which is to say that the water will go ahead and attack from the backside of the mercury, which then leads directly to the intermediate, which you are not going to isolate, but that instead you immediately process on forward through the reduction step into what is hopefully your desired material. Of course, what I've done along the way to get there is skip the acid-base step that happens first. You have this protonated alcohol intermediate first, which then gets attacked by a second molecule of water to release the desired alcohol. This alcohol, again, contains a horribly toxic, nasty mercury that you don't want to deal with, so rather than try to isolate this material, which again might be a really bad idea, but in any event is no fun, you instead invoke your magic and you throw in sodium borohydride and allow the material to be processed onto the isolable material, which is to say, again, you make both enantiomers of this alcohol, and the mercury is replaced by a CH bond, and there it ends. So anyway, why do we use a nasty reagent? Well, it allows us to accomplish a transformation that does not work as effectively as you'd like without it. So in other words, we're going to use this material if it works better than the other tools we have. And that's going to be something that you encounter a lot in organic chemistry, that there are tools that have limitations for whatever reason. So it's always useful to come along and develop other tools as well. And in fact, many of the reactions that we're teaching you now are very, very old reactions, and in practice, I haven't run many of these because there are better tools available now. This is simply the tool that was available first, and then people have refined them over the years and so on. But all of those refinements tend to be with things that are nastier, but give you some other additional advantage that make it worth doing. The higher yielding allow you to avoid some other nasty byproducts and stuff like that. If a carbocation causes a problem, then presumably you can change your mechanism, avoid making a carbocation at all, and therefore you can achieve these desired results without running the risk of rearrangements. Why do oxymercuration reactions in the first place? Well, because possibly your normal acidic addition of water or methanol or whatever alcohol to make the ethers is going to be one that suffers from rearrangement type chemistry, and you're looking to avoid it.